The pressure, we know it as like 1 atm.
Ah, 1 atmosphere.
Yeah.
This is 1 atmosphere. Good.
And rho, we can estimate like, what would be the density? Like the density of water vapor at this temperature, I guess, close to that. And from that, maybe we can.
Good. So you're saying if I know this and I know this, just do the ratio. It's a good way. I'm going to do the estimate quickly in a different way, and then we go back there. Okay? And how quickly, I don't know. Depends on how I do it. I would say I do it this way. So let me check first dimensions. Pressure, I can think of it as force per unit area. But if I use PdV, like work, then I can think of pressure also as energy per unit volume. That helps. And then rho, I'm going to think of rho as energy density. That's what is there, energy density. Energy per unit volume. And so the two are the same dimensions, which implies dimensionless. Okay? That's the first thing I have to say. If I want to estimate it, I have to know at least what are the dimensions. Don't confuse dimensions with units. No, independently of units, it's dimensionless. Now, note also that if I call raw matter the mass ink, so raw matter C squared is what I call rho. And so when I write P equal W raw matter C squared, I'm going to put the C squared here. So I'm interested in this quantity, and I'm interested in this quantity for air in this room. So if I have to give a guess for my estimate, I'm going to say, let's suppose we have speed of light squared. What's going to be? There has to be some property of air as to the dimension of speed. What is it? Speed of sound. Come on. It's sound that goes in. The sound. Speed of sound is about 300 meters per second. Here I have 3 times 10 to the 8 meters per second squared, 10 to the minus 12. That's my estimate. If one was nice, 10 to the minus 12. 2 minutes. Do you believe the number? 10 to the minus 12. You saw what entered, so I needed an argument for saying should go with the square of the velocity. I use this one, dimensionless times C squared, but air certainly doesn't depend on speed of light. And so I should cancel another C squared. So now I know that W goes as a speed squared and speed of work. Air as a speed is the speed of sound in air. Speed of sound in air, I know, 330 meters per second. Speed of light, I know, done. So if you say 0, it's a better guess than saying 1. No? Radiation, thermal radiation is 1/3. Dust that is pressureless matter is 0. And here it's not pressureless. So as I was saying, well, this we know it's 1 atmosphere. This we know, you take the ratio and you get something. And I say, if you do it, you get 10 to the minus 12. Okay? Yes.
I still don't understand why you would put C squared in the first place. Why rho equals rho m C squared? Oh, okay. That's the pattern. See?
Yes.
I see.
Yes. And I'm using it. So I did first dimensional analysis to find the dimensions of W. So I learned that pressure and energy density have the same dimension. Did I need to do it? It's already written here. Okay. And second, energy density has a C squared, but air is certainly not relativistic. So this should better cancel out. What do I learn by that? And I learned that if it depends on a speed swim a square. And so I got lots of physics out of very few things. I could have said, well, I know the physics of fluids. I know that the speed of sound is the square root of, you know what I'm going to write here? If you have studied how sound waves propagate in a fluid, you know that they are what? They are perturbations in pressure when you put in energy. And so what I wrote here is that P, I should not write P, we should write rho, and I should even write rho matter. To perturb the mass density, it changes the pressure. You have this pressure wave. There's a wave equation with the speed of sound, and there's something to be done a bit more carefully. That is, when you do this, you have to ask if it's adiabatic or if the entropy changes or the energy changes. And Newton got this wrong and got the speed of sound wrong by a factor of 2 because he thought that sound, that are pressure waves, are transported without changing the energy. But in fact, the energy changes. It's just that they are fast enough that the entropy changes. So this is a fixed entropy of the gas. And that's important. You get up, you know. But what I did is, oh, come on. I just need an estimate, P over rho m. The derivative this with respect to this, my estimate was, forget the derivative, it's just pressure of the gas. It just took away the delta there, and even yes. Okay? So if one is precise, out of this, one will get something, which is 10 to the minus 12, but with the number in front correct. Okay? Do you believe it yet? I'm going to do it 2 more times. I want to make sure that this number is clear. Let's do your way. The way is, P we know, and rho we know. We write them and we take the ratio. P is,
One of what's very
okay, but I need it SI, international system. P is kilopascals. Kilopascals. You all know that Pascal is the SI unit, is Newton per meter square, 10 to the 5. Don't believe it? You check. Pressure, where is pressure? Bit low the pressure today, 170 at 2 Pascal. Okay? So 0.97 of the thing that I had. Okay? Good. Like maybe the rain is coming, the pressure is low, and things are coming in. Generally is 1.1. Yeah, nice. Okay, this we are. Now on this. Okay, so we need to do W, that is E over rho. We said is rho m c squared. What is rho m in this rho? In a meter cubed. What's the mass of air in a meter cubed? Maybe this I should do for once. Don't say it yet, I want to see mass. A, 1 milligram meter cube. E, 1 gram meter cube. C, 1 kilogram meter cube. I'm going to stop here. A, B, C, should we do it again? Think again. We do it again. Like, you swim in air every day. Do I have to sit and do the speech? You swim in air every day. You are physicists. You are good physicists. You ask hard questions about things that are. Well, how do you train about the hard things? You train by asking questions about the things that surround you. You make sure you know them completely.
Water is 1000 kg per meter, right?
Get
So air is like 1000 times less, I guess. So 1 kg, yeah.
1.2 kilograms per meter cube. 1.2 kilograms per meter cube. Okay? And let's check. No, it's important. No, you see light every morning, you know 10 to the 26 watt from the sun, because it's 1 kilowatt per meter square. If you float in there all the time, and you know that if you're a meter cube, but it's pushing you 1 kilogram, that is the cube. Okay? Okay, so let's put in numbers. Let's see if we get back this state. So W equal P over rho matter C squared. P is 10 to the 5 Pascal. This is 1 kilogram times speed of light squared. 3 10 to the 8 is 10 to the 17. That's good. Okay? Do you believe it? Should we do it one more? I mean, it's here when you need to. It's here when you learn how to do order of magnitude things, because there's everything. There's things that you see all the time, things that you are learning, you know, because you do them all the time. Let's do one more. If you really believe it, we should get again the same result. P times V equal. I like it this way. I don't like R, small r, because I know what's okay. I should be able to do it again. I P on the left hand side. Then I have KT times N over volume. I wrote the same one. Here I want the density. How do I get the density? I put a mass. Let's say MC squared. So I have to divide it by MC squared. Now this one is rho, and this one is W, right? 15 over MC squared. M of what?
One molecule.
Molecules in air. In air, there's mostly nitrogen, and then oxygen, 70% nitrogen. Nitrogen, what's the mass of nitrogen? Well, you say proton, I know, is 1 GeV. And nitrogen, seven, nitrogen is number 7. Then you need also the neutrons, so 14. But this is molecular hydrogen, 24. Right? 38, thank you. And KT, this rule, we know the temperature, but I want the KT. This you have to have in your list. KT is, it's important, this we already did. This is going to be useful for doing cosmology. Now, when you say 3 Kelvin, quick, what is the energy of 3 Kelvin? So let's check 200 Kelvin, 300 Kelvin. What's the energy of 300 Kelvin? 1 over 40 electron volts. Easy to remember. Okay? And so you see W is 1 over 40 electron volts divided by, I don't know, 30. Well, oxygen is a bit, let's say 30. GeV, 10 to the 9 electron volt. 1000 10 to the minus 12. Okay, good. This was the fastest, right? Of all of them. Like, I'm not sure that the last one I could have done in 3 minutes, BPS. This was the fastest. But you see, it's a network of numbers. You forget one, you match it with the others. Don't forget this one. Okay? Don't forget that one. 1/40 electron volts. Because if you want to know how many electron volts is cosmic microwave background, it's 3 Kelvin. Here it's 300 Kelvin. That one divided by 100. And you have a scale all the time. Okay? Okay. Comments. Maybe exercise to leave you with general relativity, general relativity. Look around everything you see and don't estimate it with Newtonian mechanics, try with your understanding of general relativity. Assuming you've already done it with Newtonian mechanics. Quantum mechanics, ask around everything you see and do that. But do it first with the things that surround you before you do it with neutron stars or with the early universe. We are gonna need this quantity everywhere. Let's make sure that we know when we trust it and when we don't trust it. Now think about what is W for water. Okay? Comments?
So this specific estimate which we did with the speed of light in air, this like only makes sense when we have a dispersion relation like that, right? So this would not generally hold for all kinds of matter.
So this equation doesn't always solve. In fact, when you did the neutron sum problem, there was a power here.
Yeah.
There was a polytron. So this is very similar to this one. It's in the same class of this one. It's an ideal fluid. Okay? And so that should ring a bell. We're going to assume in most of what we're doing something like this, question it every time you see it. Because we're going to see what galaxies are of this form. Where instead of having molecules over, the molecules are the galaxies themselves. And we're going to do it for neutrinos. We're going to do it for photons. So poi we're going to do it for the inflaton. So ask the question as it's not a pen and paper trick, but it's something that you can touch. Yes.
So based on what you just said,
Yes.
the polytropic equation of state.
Yeah.
We don't know what the equation of state is. I think that's one of the biggest research that is being done
Yeah.
in neutron stars. Why do we go with polytropic equation of state at the first place? Because I guess this is the equation, ideal gas equation, huh? And from there it's not that big of a jump in logic. But still, why do we take it into account? And most of the papers that we read, even most of them assume some variation of the polytropic form, right?
Good, good. Yeah, so there is one first calculation theoretical to do to get intuition that is if you have a gas of fermions and you put them at high pressure, what's the relation between pressure and energy density? Find the equation of state by assuming that you are close to the vacuum. And there is something that I should probably say. Sometimes people say that Pauli exclusion principle results into a force, a repulsive force. And other people say, oh, you shouldn't say force. It's not a force. It's just the statistics. Pressure is an entropic force. Pressure is, it's more likely that molecules are pushing you in one way. You ask how the entropy changes when you vary the volume at fixed energy. No, and the generous pressure is the same question. It's just that the entropy for a degenerate gas is not the one of a non-degenerate gas. So it's an entropic force. Pressure is an entropic force. Okay? And so there you can do a calculation, statistical mechanics calculation, that P goes with a power Yeah, which power depends on what kind of statistics you have. And then once you see this and you see a few examples that all have a row to a power, then you say, oh, I'm doing phenomenology. Let me put an arbitrary power and fit it. After you have seen a 4/3, after you have seen a 1, you have seen a few, then you say, well, maybe to capture the details, I just put up. Okay, and then you fit, and you're careful not to overfit. Okay, I think we covered the two numbers that I wanted. Now we should do the shift, the jump, and ask about the foundations. And it's no secret that you have seen Friedman equation. So instead of doing the derivation of Friedman equation, I want to go to full general relativity, identify what are the ingredients, and then we're going to see Friedman equation as a special case. And I like to think of this topic as really the question of if I give you the Riemann tensor, and I ask you what's the meaning of the Riemann tensor, you have a quick answer, maybe more than one. Is suppose that I have a free particle. This follows a geodesic, there are no forces. Now I have two. They follow both a geodesic because they're both free, and they are both prepared with the same initial conditions, same velocities, but just slightly displaced. And you ask if they converge or diverge. Riemann tensor, the components that select this plane and tell you how they diverge, is what we mean by Riemann tensor. So you know the meaning of Riemann tensor, geodesic deviation. You also have other meanings, but this one is the immediate one. But when you write Einstein equations, there's not the Riemann tensor, there's G mu nu. And so I could ask again, what's the meaning of G mu nu? When we say 8 pi T mu nu. This one we know. This is energy density, it's pressure, it's shear. This we know, you touch it. No, pressure, density, you touch it. What's G mu nu? Do you have a thing that you can say, this is G mu nu, like tides are Riemann tensor. The moon deforms, the earth deforms, you deform if you fall into a black hole. But what is G mu nu? So that's what I want to cover, the meaning of G mu nu. Once you know the meaning of G mu nu, then many of the standard language of cosmology gets embedded in this larger notion that doesn't require approximation or symmetry. So I'm going to tell you first about focusing, then again about Einstein equations, and then we're going to compare GR and Newtonian gravity. This thing is not new. This thing is well known. If you read Hawking and Ellis, this is carefully explained. It's just that it's hidden in the mathematics. There's this nice essay of Baetz and Barna that make the point, but it's too much of a popularization level, so you don't get enough of the equation. So I'm trying to strike a balance for our group. So the balance I would strike is this one. We know differential geometry. We don't have to learn differential geometry. I can use it. We have a space-time. It's a manifold with a metric and a connection, and the connection is compatible with the metric. We are good so far. Riemann curvature. We have the sense of what Riemann curvature is. It's this geodesic deviation that mathematically you can think of it as if you have a vector and you transport it around a loop, and you come back and you ask how it's rotated by this matrix. Okay? This next step is mathematical. Ricci tensor is contract with this. You see, it was so nice to say what is the geometric mean of the first one. Take a loop, bring it back, and ask if the vector is rotated. And here I'm just saying contract indices. That's not geometry. That's algebraic statement. And I want to give you the interpretation on this. What does it mean, contract indices? What are traces? What's the meaning? And the message that I want to give you is that if you think about volumes and how volumes change, that's what traces do. You have seen this already when you learned that the divergence of a vector field, the divergence of the electric field, tells you how you go from a sphere to another, how the volume changes from a sphere to another, right? So let's do the mathematics now. Geometric interpretation of Ricci. Take a family of geodesics. So this is a geodesic, it's a free particle if you want. Here I have the velocity for a few of them. I can think of psi as the deviation between two of them. So I have the velocity, I have zero acceleration, tells me that it's geodesic. I have a displacement vector that is a one parameter family of geodesics. I can assume, I can impose that they are initially parallel. That means that this vector doesn't change in time at first order. And then I ask about the second order. And the theorem, for which I'm going to give you a proof, is that if you take this volume and you ask how it changes in time, in the sense of the rate of expansion, defined here in this way, no, double dot, divided by the volume itself so that it doesn't depend on the scale. And just to be clear, I already imposed that V dot over V is 0. It's this condition here. So no question about first derivatives. So this quantity is minus Ricci in this direction. And so if you want an interpretation, what is the Ricci tensor? Take this family, follow the family, check how much the volume changes at quadratic order in time. The coefficient is Riemann. Okay? Sorry, I should say Ricci. Let's look at the proof quickly. V dot over V is the divergence of the vector field, the expansion. This we already imposed to be 0. Now I take the second derivative, that is, I ask how the divergence changes in time. This is the definition. I'm asking how it changes this V dot over V. And now the trick is, you see there's two derivatives. Exchange them, antisymmetrize them, go back here. You see that the antisymmetrization gives you Riemann. Substitute it inside, then check how things are contracted, and you find that it's Ricci scalar. Some algebra, you can do it, I don't know. Okay? And so if I have to read it again, and I have to give them a name, people generally take this minus and they put it on the other side. And instead of saying that the expansion or the defocusing is minus Ricci scalar in the correct direction, they say the focusing, where you put a minus and say focusing means it goes this way, is minus V double dot over V. And this is sometimes called the focusing equation. Okay, with the minus on this side, and they say F equal R mu nu U mu union. Okay? And then up to here, this is only geometry, and then you want to do gravity, and that the gravity focuses matter. So this is R mu nu. Now I want to do Einstein equations. Second step, I should slow down. Do you have questions about the geometry? Yes. Yeah, ask again. Are you asking about this one?
Yeah.
Okay. So, yeah, I have to convince you of this one. Let's do it in Euclidean space. Maybe I convince you of that one first. Take a sphere that has some volume, and then take another sphere that has another volume, and take the vector that points from one to the other. This is a vector V. Now there's a claim that I'm going to make that the divergence of V is bad notation. Vector, vector, volume, volume. That is, divergence is the rate of change of a volume. And this is the same equation. So if I want to convince you more carefully, I would have to do something like this. Say, well, volume, I can think of it as square root of volume density. And then I'm asking how V dot is the derivative dt of volume, that is the derivative of this one. And I'm dividing by the volume itself. And then there's this relation that we have seen when we proved when we found the boundary term for the action is 1 over square root of h d mu square root of h v mu. This is the same as the covariant derivative. And this is the equation that I'm using. I'm saying this divergence is exactly how the volume, the logarithmic change in the volume. And if you are not convinced yet, the suggestion is really think of divergence of the electric field as if you have a sphere and there's this electric field pointing outside the sphere, it goes from one to the other, showing that the divergence of the electric field is by how much you have to go from a sphere to another. Yeah, and that's one special case where it becomes complicated. Or another way would be you say volume, and write it more carefully as integral over a region square root of a. Volume is integral over a region square root of h d3x. And then v dot is choose a vector u mu, and you derive with respect to u mu the volume. This is v dot. And then you plug in this one, and you should show that you get this in the limit where this region is small enough. That's a more straightforward calculation. And in the same sense, to take the double dot, that's what I said, what I did. No, I said you take this one, and then you do one additional derivative in the direction of time. There was another, and yes.
I was wondering if you can explain the electric field analogy. And the potential.
Yeah. Okay. So take a charge, take a sphere. On the surface of the sphere, you get an electric field. We all learned that the divergence of the electric field is the charge. But we don't need it for the moment. That's dynamics. I only need the meaning of divergence. Okay. So I'm saying this is the same as v dot over v, where this is a sphere of a certain radius. Now I go out by a certain amount that is given by the electric field, and I ask, what's the volume here? And I say that the change in volume over volume is given by this quantity in the limit where you are moving this just by a little bit. And so I'm saying, if you haven't done it, go back to Maxwell equations and ask what's the I should say it this way. We're asking a difficult question. We're asking what's the geometric meaning of Einstein equations? That presupposes that one has asked what's the geometric meaning of Maxwell equations. Likely you have been introduced to Maxwell equations in two ways. One is differential and one is integral. No, you only have loops, you have spheres, you have this is what I'm doing. I want to do Einstein equations, integral version, not differential. That's what geometric meaning is. Okay? And so as you can see, I have one piece. Okay, let's do the other piece. Now I need Einstein equations. Forget the cosmological constant, forget this c to the fourth for the moment. I'm gonna put them back later. The first thing to do is we got a meaning for this one, not for the Einstein tensor. I'm going to argue that it's easier to interpret this one than the Einstein tensor. And so what do? You pay back. You say, I just have to reverse a trace. I pay it back this way. If you do it correctly, you can also subtract the cosmological constant. So this is another way of writing Einstein equations. Completely equivalent. If you're not convinced, check. You contract everything with G mu nu, everything. And then you sum exactly what you need to get back on this side, just R mu nu. Okay? So now on the left-hand side, there's just geometry R mu nu, and everything else is on the right-hand side. Second step, let's choose a frame. A frame means that there's some word line. Doesn't have to be geodesic, but I'm going to assume it to be geodesic now. It carries a clock, so it has a 4 vector. When you contract T mu nu with the clock, you get energy density. When you contract it with two things in a spatial direction, you get pressure in that direction. Okay? When you contract it mixed, you get either stresses or energy fluxes. Okay? Don't forget, T mu nu doesn't have the components of T mu nu cannot be measured. What you can measure is you need two things. You need T mu nu and the detector. You contract, you get an invariant. Now this is a matrix where the matrix is over these big indices. Okay? Okay. And so you see what I'm doing? I'm getting rid of abstract tensors and building things that you can actually measure. So when you contract this one on the left-hand side with clock, you get V double dot. How volumes change. When you contract it on the right-hand side, you get rho plus P. You see, this is a trace. That's what I did also on the left-hand side. And so you see, if the pressure is the same in all directions, this is 3P. But if it's not the same in all directions, this is the sum of the three. That's the origin of the three that you always see in some equations, but not in all equations. And then you also get a lambda here at the end. And so this equation is called the Raychaudhuri equation. Let's add some remarks. First, forget the cosmological constant. You see here there's a minus. Energy density is positive, come on. Pressure is positive, come on. So all of this is positive, and here there's a minus, it means that gravity focuses things. If there is nothing around, gravity cannot focus. So if you start converging, you keep converging. If you start diverging, you keep diverging. But if you start parallel, you do have deviation of geodesics, no doubt. But these volumes don't change. Deviation of geodesics is about, you can have, Riemann tensor can be non-zero in vacuum. Ricci tensor in vacuum is zero. Okay, Ricci tensor tells you about how volumes change. And so every time you pass through a region with matter, you focus. Unless for some weird reason rho was negative, or for some weird reason 3p was negative. In fact, what you really need is that all of this be negative. This is one of the energy conditions. Rho plus 3p, one sign or the other, this is an energy condition. Rho plus 3p positive is the good one. Now you see it. Then there's lambda. Lambda is not matter. Lambda is part of the geometry. But now let's look just at the effect of lambda on focusing. Ordinary matter always focuses. A positive lambda defocuses. Positive lambda would be something positive. Now, one would say, well, but there's this one, this wins, this is bigger. And so it just takes away something. But suppose that this one has diluted so much that you can neglect it. Then this one wins. And you get the universe defocuses. That's what people say when they say it accelerates. Acceleration of what? Of this thing. Okay? This is the thing that accelerates. Yeah, maybe I should write an equation now. V is square root of h, which is a cubed in Freeman-Robertson-Walker. V dot over v is 3 a dot over a, 3 upward rate. Okay? That's the velocity. And then I'm speaking about the acceleration. A double dot over a with some 3. Okay? Questions? Yes.
About the basis.
Yes.
How do we know that this is what the observer at that point sees?
Say it again, I didn't
How
catch
do we
it.
know that this basis describe, what the observer at that point sees? Their what line?
I'm not sure I catch the question yet.
We're trying to say, when projecting
Yeah.
TVU onto, the spaces. Pressure makes sense, rho makes sense, in their frame. But it's hard for me to understand how the spaces would make that happen.
Okay, I think I'm starting to listen. So there's some geometry that gives this rich scalar. There is some matter that gives this energy momentum tensor. Now, there are two separate questions I can ask. I have a detector that measures energy density and measures pressure. This detector has a word line, this one. And so out of that, I can measure each one of these ones. Okay? Then I have to ask, how do I measure volume? And so to measure volume, I would need think of these trackers. I would need many of them. So I could think of, I don't know if we did this exercise. I could think of some dust. I could think of, I don't know, sugar. I prepare it in, or like a cloud or something, and then I follow it. Okay? I follow it and I ask how the volume of that cloud changes. And so the first statement that I'm making is that Einstein equations tell me that if the rate of increasing volume is measured, and if the energy density and pressure are measured, the two are not independent. Einstein equations tell me that they are related. Now, if I understood your question was, wait, but you're adding an ingredient that we never think about. We always say Einstein equations without saying what is the this extra thing that I introduced. And say these Einstein equations provide the answer for all possible measurements. And I'm describing them more concretely by taking one measurement that is arbitrary. And so now I could change it. I could say, well, suppose I was moving this other way. Then I would say the pressure in one direction to be larger and this one to be maybe different. And the energy density to be also different. And the volume different, but the equation still holds. This equation is going to hold for all observers. It's just that the single terms are going to change values.
But why this specific set of bases? Like, why is it you being the timeline vector?
Okay. So okay, this is important. I'm making the step of saying, take mu, this tensor. Let's avoid the completely standard mistake of saying T00 is energy density, because energy density is something a detector measures, and two detectors in motion, one respect to the other, they find different values of energy density. For instance, a tennis ball, if the detector is going towards the tennis ball, it has a high kinetic energy. If the detector is at rest with respect to the tennis ball, it has a zero kinetic energy. So the energy is not a property of the tennis ball, it's a property of two things. And so T mu, we call it the energy momentum tensor of matter, but when we measure energy density, pressure, stresses, it's really the contraction of two things. And so the thing is the detector, and to think of the detector as T mu is the model for matter, the model of the detector is always at least word line of the detector, clock of the detector, and accelerometers that tell you principal directions for the detector. Okay? And you can really think of it as, a tank, a calorimeter. This calorimeter, you move it around, and then a particle enters, it's absorbed, and you check the liquid in the calorimeter, how the temperature went up, by how much. And it clearly depends not just on the particle, it depends also on the motion of the detector. Okay? And the same, the volume. The volume depends on, it depends on this family of detectors, this dust, this gas, this. I don't know if we did the problem of coffee or sugar in the ISS, how the volume changes. You did this, right? Yeah, so that was this calculation, yeah. Yes.
So we can say that the Einstein equation is complete, but it also tells us something about the equation of state.
It doesn't, because I haven't given the relation between the two yet. No, like you can put any equation of state inside here. No, so I would say the equation of state is still unconstrained.
Okay, so that's just one of the constraints on the equation of state rather than all of them.
I would say this is no constraint on the equation of state. You can put any equation of state that you want.
Oh, okay.
This relates geometry to matter, but matter is still unconstrained. Apart from, like, if you take matter that has all of this negative, then you will see that this doesn't focus, but they focus. But maybe it's also okay. Sometimes it is. Okay, next step. Did we learn something new? Have you done already this calculation when you did Newtonian mechanics? Because you could have done all of this in Newtonian mechanics. I don't know if you were taught Newtonian mechanics this way, but let's do Newtonian mechanics. Because if you want to compare Einstein equations to Newtonian mechanics, and you're using different mathematics, you're never going to be able to compare them. So let's do Raishaduri equation of volume expansion in Newtonian mechanics. What do I need? I need my sugar dust. I let it go, I follow it, and I ask, does it converge or does it diverge? If there are no forces, it should keep going. And so the volume shouldn't change, just by inertia. So what I need F equal ma. I'm going to assume that there are no other forces besides gravity. Gravity is this force that satisfies this equation, where this is the source. All familiar, right? Don't have to explain this. What is expansion? Divergence of V. What is the rate of expansion? That's the name I use for this. Rate of expansion. Expansion, rate of expansion. Well, you take a derivative. Derivative, this, we are in Minkowski space, we are in Newtonian space. Derivative goes in and gives you acceleration. Acceleration is F over m. F over m is grad phi. So you get divergence of grad, that is Laplacian, that is rho m. So what did I just prove? I proved the same equation that we had before. Expansion rate equal minus 4g rho m. This is Newtonian gravity. What does general relativity tell you? Expansion rate is equal minus 4g rho m. But pressure also contributes to focusing. If you have more pressure, you're going to focus more. In Newtonian mechanics, pressure doesn't gravitate. In general relativity, pressure gravitates. And also you have lambda that you didn't have before. Okay? And now you see I restored factors of C, because before I had a C to the fourth and a 1 over C squared because there are these two dots. So now I'm being a bit more careful. So this is like time derivative. So dimensions of 1 over time squared. And so here you get really raw matter, but then you have to pay. And so often people use this intuition of if you have a cosmological constant, how quickly volume expands. And the point is not really expands, accelerates. Because now in Newtonian mechanics, we have an intuition for these things. No, like if you start with a velocity, you keep that velocity. So let's start with relative velocity 0. A volume that like the derivative here is 0. Now I have my dust, it's at rest, and then I ask if it accelerates and converges at focusing. It focuses. And so I can ask over what scales it starts focusing. And if there's no matter, it doesn't focus. If there's matter, it's going to focus. If there's a cosmological constant, It's gonna focus. You see, I'm never speaking about the volume of the universe. That's the message. Don't think that the universe is expanding in the sense that the whole universe is a ball and this ball is changing in volume. The universe could be infinite. Like, as far as we know, it's larger than any bound that we have, and so why not just assume infinite as a mathematical simplification? The physics shouldn't depend on that simplification, something we don't measure. So the statement is really, if you have your sugar and you follow it, how long is it gonna take to occupy twice the volume? If it's just cosmological constant. And if it's galaxies, that we're saying it's not very different from sugar, because they don't have any like pressure or intergalaxy forces. We are neglecting everything. And so now I need numbers. Lambda, do you have lambda quick? I need lambda quick. How do you get lambda quick? You have to have it in your list. We need all of this, no? We need this, we need this. We don't need this. This we know how to take into account. So how do you get lambda quick? You agree that lambda, this is 1 over time squared dimensionally, right? So this should be 1 over time squared. And so as a time, 1 over square root of lambda c squared. Forget the c squared, 1 over square root of lambda. So what is this t? How big is this t? In a number for lambda, say, just need a number for this, 1 over square root of lambda. Like if I ask you to estimate something in dimensions meters to the -2, we have an intuition. But if I ask you to estimate something in dimensions of time, you should have to pick. What could it be?
So it should involve the speed of light and a length scale.
Yeah, that's the question.
Oh,
So this once I say, I would say you cannot forget it anymore, because there is a number that you know. What's the age of the universe? Say that 40 million. 40 million years is equivalent, right? And what dominates the expansion of the universe today? Well, lambda and matter more or less same order. And so if you have this, you just guess immediately, 10 billion years. 10 billion years, that's 10 billion years. Billion is 10 to the 9. Years is 10 to the 7 billion. Seconds, and so we have 10 to the 17 seconds. So lambda meters. So lambda meters, lambda is 1 over where is square. Okay. Open off, I can get to the next two is the better number. I think if I put the 3 here, I think I should have somewhat like this number. It's okay if you don't remember this number. But this one you have to know because you get it quick. No? Yes.
But that really only works because it happens to be approximately as common as.
Yes. So I'm using one thing, one story that is to remember, that is flow, not just the one of matter, but I would say but still good enough. Raw matter and lambda. this equation, they contribute the same way. So if I take all of this piece and all of this piece, it's this story of when they put a pie chart and they say, oh, this part is lambda, this part is matter. You see that pie chart, you can tell that that pie chart is, they are not squeezed, they are not 10 to the minus 3, 10 to the minus 6. That's the only information that you need. Okay? And don't forget that pie chart is about today. In the past, this was huge, and this one didn't change. Okay? Okay, so we did a lot of cosmology without ever doing cosmology. And some remarks. Gravity attracts. What does it mean that gravity attracts? That this thing is negative. When people say gravity attracts, in Newtonian gravity, they mean that this is negative. In general relativity, they say this thing is negative. Well, unless there's this piece. Okay? Newtonian limit. Well, when is Newtonian limit going to work? Certainly, you need that you can neglect pressure so that you go back to this one. But to neglect pressure, you need the W much smaller than 1, for instance, 10 to the minus 12. Okay? Or if you want, this is a better way of thinking about it, speed of sound much smaller than speed of light. Okay? And so we have this W. If you see something like W equal 2, be suspicious. It means there's a speed of light, sound that is twice the speed of light. W should better be smaller than 1. Okay? Yes.
What are we taking it as a constant? Del P by del rho by
Entropy.
so how do you define the entropy? That entropy depends on where you are, right?
Yeah. So yeah, this is a fluid. It's a fluid that has is in equilibrium. So it has a rest frame. You assume it's in equilibrium, so you can speak about the entropy of the fluid. This is a really Newtonian argument. Okay? I'm really speaking about air in this room. And then we did look at Tolman, Oppenheimer, Volkov. Well, that's again this equation. If you check, this was the relevant quantity. It was just written for a spherically symmetric spacetime. So if you do these spheres that are spherical, we didn't study singularity theorems. Singularity theorems are the statement that once you get to a certain density, then there's a mechanism that doesn't stop gravity from forming a singularity. That's the statement of if matter has the property this is positive, then this is negative. So if you start focusing, you cannot stop focusing. So you're going to form a singularity. That's the singularity theorem. Okay? You can use it also for the universe. You say, well, if you go early enough, well, you can neglect this one because energy density and pressure are large. This energy density and pressure are such that the sum of the two is positive. You go back in time enough, you get, not that the universe becomes a point. That's not the statement. Is that if you take any volume, that volume converges. Okay? Assuming that there's no force that pushes out. These were geodesic. Okay? Cosmology. That's going to be the topic for a while. This is the statement that I would add there at the blackboard. And I think it's good. I think what we have to do next time is discuss if we assume Freeman-Robertson-Walker, then yeah, we don't even have to declare anymore like which volume. We're just gonna say Freeman-Robertson-Walker, there is a special set of word lines of observers that are the ones that see homogeneity and isotropy. So we stick to those. And then you can speak about a region, but yeah, if you say the volume is some coordinate volume delta x cubed sine physical scale. This delta x cube is always going to cancel between the two. And so you always have things that you can write as Hubble rate and ratio to the equation, something like this. And here on this side, these are going to be energy density and pressures measured by these cosmic observers, if you want, in the frame of the galaxies. And we are going to need the equation of state. We are going to need to think about, given an equation of state, what are the typical behaviors of the scale factor, and also what are the typical time scales. We still have some time for discussion. Yes.
So typically, cosmology, we talk about moving volumes.
Yes.
Is that be the same as that?
Exactly. That's exactly that. It's exactly. So now you see that you can do it even outside of cosmology, but you have to declare what is the family. And so in cosmology, you do it for the family that if you want take the cosmic microwave background, we see it's 3 Kelvin in every direction, but we are moving at 200 something kilometers per second. So if you check, you get the photons are blue shifted, the ones coming this way, and red shifted, the ones that come the other way. So when we say 3 Kelvin, we mean there is some observer that sees the same wavelength in every direction. Those are the Kumumi. Okay, so we are not Kumumi. But this framework, yeah, doesn't assume that. And as you can see, I had 3 different ones. Okay. Yes.
In general, I think the Right-Chudley equation, it also captures how these lights are shear and how they have torsion.
Yeah.
But because we have broken down into like explicit component form, where we have like evaluated the stress energy tensor.
Yeah.
How do we see those from this form of the Right-Chudley equation, the torsion and the shear?
Yeah, I see what you're saying, and there is first of all something that is a freedom one has in choosing this bundle of observers. So I chose that initial conditions so that first of all it's geodesic, and second it's a few of them and they're all parallel. And once I do that, then there's no of those terms contribute.
Where did we make that assumption here in our discussion?
Yeah, it was here at the beginning. It was at this level here. It was this condition here.
Okay.
Okay.
Yeah.
And then there's another thing that is worth knowing. I'm doing a Right-Chudley equation for timeline things. You could do it for null rays.
Right.
That's another important thing. It's also called Right-Chudley equation. You don't get this equation, no? And then it's important here. So it might be that you were referring to that.
If we have an initial congruence of that form, like everything is like, yeah, they don't have any, then it can never have any shear, like they can't.
Oh, I see what you're saying. No, okay, good. I understand your question now. I understand your question. For sure they can shear, but I'm asking a simple question. If they shear, I only ask about the volume.
Okay.
Okay. And so if you want, you can write this shear tensor, and it's just a trace that doesn't know about the non-trivial shear. If I don't, before I decompose it, there's some B mu nu tensor that has a component that is what you're saying, shear, that is zero trace.
Right.
And I'm really looking at this thing that is the trace of this.
Got it.
Yeah. And so inside here, they could shear, but shear doesn't contribute to the volume change.
Right.
Good that you brought it up. Yes.
My question, but what do we think of when we say co-moving frame? Because one of the two ways we look at movement of the particles is I think Eulerian and Lagrangian. And that basically tells you like what equation you use to look at the volume, whether you look at the particle, one particle in the system or
Yeah.
a volume of particle, I think. Or
Yeah.
writing a Hamiltonian basically.
Yeah.
So
Yeah, I think I understand your question. So first of all, separate this language of fluid dynamics from the one of general relativity, because there you have less symmetry. You have the fluid that sets a frame, and now you can ask observers that are tied to the table where the fluid is moving or tied to the fluid. But for space-time, you don't have the two. You don't have the table and the fluid. So you have to make an intrinsic reasoning. You just have to tell me, I have this word line, are there forces acting on it? No. And then I don't have any other choice. You have to give the initial conditions, but then given the initial conditions, I can only follow it. And so when people say co-moving, they are adding to this picture one ingredient, that is, if you assume that your space-time is homogeneous and isotropic, then this is a symmetry. You are saying that there's no preferred direction and there's no preferred place. And so now there is only one set of observers that are an axis of symmetry for them. So that's what people call co-moving. And maybe we should go back to this. Co-moving is a statement that is tied to symmetries. Without the symmetries, you cannot, co-moving doesn't have a sense here. And I understand in fluid dynamics, you have these two notions, Lagrangian and Eulerian, and yet they are not present at all, because space-time is not a fluid. You can still say with respect to the fluid. Yes.
Do we expect them to be a little bit different at different places of the universe?
This one? Good. Yeah. So the answer is yes, first. And second, the derivation here, I never assumed that this applies to the full universe. This is for a region. And so change the region, you find a different volume change. This applies near a black hole. You would say, I'm near a black hole. There is matter around the black hole. And I now ask how volumes changes. So when we apply to cosmology, the first assumption we make is assume that at large scales, things are homogeneous and isotropic. And so if I do it for regions I find that are co-moving, I find the same answer everywhere, so that I don't have to declare where I'm doing it. That's the first statement. But that is not something that's going to hold at all scales. It's only for averages over long scales, homogeneity can be solved. Because for sure, the solar system is not homogeneous and isotropic, and the galaxy is not homogeneous and isotropic. So you have to go to scales that are much longer than galaxy. And so to answer again your question, this rate of expansion depends on the point, but if you take volumes that are large enough compared to the scale of galaxies, then at some point it doesn't depend anymore on the point.
What about the scale of the large scale structure?
That's a place where one starts separating things by saying, well, now let's discuss the average, where this is the same everywhere, and perturbations on top of the average, so that you think of them as perturbations, as a density contrast. And so you break you take this one that would depend on the place, and you separate it into a background quantity and a perturbation. And so we're going to do something like this, but not for large scale structures, but for primordial perturbations. Or if you want, CMB is 3 Kelvin. But 3 Kelvin, if you average over scales larger than degree, but below there's this 1 part in a million temperature fluctuations. And so we're going to say, oh, 3 Kelvin average. Let's try to describe now the perturbations of the Kelvin. Let's try to derive them. And one can follow the same logic for large scale structures. CMB is easier because it's linear, large scale structures are non-linear, so the question. Okay, I think we are too close. Thank you. That's all for today.